Okay, hello everyone. We're just going to go over some electric potential and electric potential energy questions today. So starting with question number one, says a uniform electric field with a magnitude of 500 newtons per coulomb is directed parallel to the positive x-axis. If the potential at x equals 5 meters is 2,500 volts, what is the potential at x equals 2 meters? So the first thing that I did when I saw this problem is draw it out. So if I have a uniform electric field and it's going in that direction, and I have two different points, I have two different points at 5 meters and at 2 meters. So I just like visually, I have like an idea of what I'm looking for. And so then what I did was I had to figure out what the information I need for this is. So it's asking me for the potential at 2 meters. So obviously I need to find the change in V, the change in volts in order to solve this question. So the change in V is equal to work over the charge, right? Which is then equal to the force times distance over the charge, which is then equal to EQD over Q. Q's cancel out, and you're left with ED. So now that I have the summation, I can look and see what I need to plug in order to find the change in V. And remember, this is really important that it's the change in V because that's like important to answering the question. So I know that the magnitude of the electric field is 500 newtons per coulomb. So I have 500 times, and the distance or the change in distance is 5 meters minus 2 meters, which is 3 meters, right? So then the change in V is 1500 volts. So what does that mean? That means that the change in V went from something to something minus 2500 is 1500, right? That means that V final minus V initial equals 1500, right? So if you know that the initial is 2500 and that's 1500, you can add 2500 to both sides and you get that V final is 4000 volts. That's the answer, right? I think so. Yeah. Okay. And then let's see. So these are more some theoretical questions. So it says an electron moves from point I to point F in the direction of a uniform electric field. So before answering this question, you should probably know what the positive and what the negative side looks like. So let's say we have a capacitor which has an equal and opposite like magnitude and direction. And I have a positive side and I have a negative side. So based on what you've learned in electric fields, you know that it's going to point in this direction, which means that if the electron is moving in that direction, it's actually moving opposite to the direction that it wants to move, right? Because the electron wants to go to, since the electron has a negative charge, it wants to go to the positive side. So automatically, you know that your electric force, and the distance that is occurring are in opposite directions. So if you really want to think about it that way, you could think of it as cosine of 180 degrees, which is also -1. That's one way of looking at it. Or you could simply just identify that since the electric force the the distance are in opposite directions, the work done is going to be negative. So let's make sure that we get rid of the ones that say positive. So that's A, and C, and E. So the next thing that you want to do is figure out if potential energy is increasing or decreasing. So what happens is that you have the maximum stored energy when you bring two like charges apart, because as soon as you release it, all of that stored energy is going to be transformed into kinetic energy, ideally infinitely far away, right? So we know that the potential energy is going to increase as you bring the negative charge towards this negative field. So the answer is B. Okay. And then Shreya, do you want to do this next question? 11.
Yeah, sure. So the question states that if 500 joules of work are required to carry 40 coulomb charge from one point to another, the potential difference between the 2 points is, so um, we can write this formula saying change in V is equal to the work done divided by the charge. So here we know that the work done is 500 joules, and we also know that the charge is 40 coulombs. And joules over coulombs, so anyway, so we know we're doing the right thing. And when you solve this, you get 12.5 volts. And that's our answer.
Okay, so let's go through 14 through 22, which are some pretty hard theoretical questions that we have. So looking here, number 14 already has an answer on it, but it says, at which of the label points will the electric field have the greatest magnitude? So um, electric field is the force over the charge, right? And you know that force is sorry, this is force is KQ1 Q2 over R squared, right? Times 1 over Q. So one of these Q's cancels out. And so ultimately you're left with, I'm going to move this up here, E equals K KQ over R squared, right? So what this means is that where the point has the least distance, right? Um, it would have the greatest electric field, right? Greatest magnitude for electric field. And since I appears to have the least distance, that would be the answer. Because let's say you were to look at like this point over here, and let's say it's way farther than I is, which means that on the denominator, you're going to have a bigger R squared, which means that your magnitude would be less. Okay, and then this one says, what is the magnitude of point A? So the way that you would do this is looking at the basically the force and the charge, you would have to figure this out. So you know that the change in V equals um, what is it, work over Q, right? Which is then FD over Q, which is then EQD over Q, which is then ED, right? So based on that, it says, what is the magnitude of the electric field? So at A, it's 30 volts, right? 30 volts equals E. And the distance based on the information that we're given is 0.3 meters. So if you divide both sides by 0.3, you get that the electric force, or yeah, the magnitude of the electric field's force is 100 volts per meter, which is answer choice A. Okay. Um, and then for 16, I think Shreya, why don't you do that one?
Yeah. So it's saying, at which of the label points will the electron have the greatest potential energy? So you have to figure out that change in volts is equal to work over charge. So you're basically trying to solve for the work, um, which means that you need to find the uh, change in potential that's the greatest. So in this case would be negative 70 volts. And then you also want to be also be able to check all the points near that. So the only options here are I and H, and the answer is going to be actually H because it's not necessarily it's asking for the greatest potential energy. So H is a positive test charge being attracted to a negative. So therefore, it's going to have the greatest potential energy rather than any of the other ones because it's the one that is approaching the negative 70 volts.
Also, doesn't I revolve around the circle or like the field itself with negative 60 volts, whereas
Yeah,
H is negative 70. So
yeah,
you could say that the magnitude of the potential energy is also greater, right?
yeah.
Okay. And then what is the direction of the electric field at B? So when solving this, you have to consider what side um, each side of the electric field is. So if you notice, the voltage is positive here, which means that it's the positive end of the spectrum of the electric field. And then the other side is negative because the voltage is negative here. So that means that the direction of the electric field is going to be away from the positive charge. So if you were to kind of draw a line, it would be something like that, right? So if you looked at the direction of the electric field at B, so B is on this positive spectrum. And so in that case, it's going to move away from D. I mean, it's going to move it's going to move towards D, right? Because it's going to move in this direction. It's going to move left away from this positive spectrum. So if it moves away from that, then it would be towards D, right? Are there any other reasons it moves towards D, or is it just because of the capacitor on that side?
It's also because it's a positive and it wants to go towards the negative. Yeah.
Yeah. Hmm. Okay, and then a positive point charge is placed at F. When it is released, what would happen? So, like I said, oh, sorry. Like I said earlier, the left side is the negative side because of the negative voltage. Really quickly, let's maybe like go through why it's the negative side. So change in V equals, remember we said ED because, so that means that if this is negative, that means that the change in the voltage would also be negative, right? So if this is negative, and you said that you place a positive charge at point F, what would happen? So if you place a positive charge here, it's going to want to go towards the negative side, right? I think,
Yes.
yeah. So then it would say a force will cause it to move towards, wait, it's gonna want to move toward, wait, why would it move towards E?
Um,
Or would it move away from E? It would move away from E.
which one for 17, right?
Yeah, I think it would move away from E, I think.
Yeah.
Yeah, the reason it would move away from E is because the positive charge is going to be attracted to that negative side of the uniform field. Because remember, opposite charges attract.
Mm-hmm.
So here, yeah. And then how much work is required to move a -1 microcoulomb charge from A to E? So let's take a look at this. So it says from A to E, that means I'm moving from 30 volts to um, E is 40 volts, right? I think, yeah. So I went from plus 30 to minus 40, right? And so it's final minus initial. So it would be -70 volts, right? wait, let me zoom into this so
Yeah.
that I can. So we said that it's plus 30 and minus 40. So remember, with voltage, it's going to be final minus initial. So it's going to be negative 70 equals work over Q. So Q is negative 1 times 10 to the power of negative 6 coulombs. And then in order to find the potential energy or the work done or the work, you can multiply those two together and you would end up getting 7 times 10 to the power of negative 5, sorry, coulombs. And is it positive? It's positive, right?
Yeah.
Okay. Let's see theoretically why it's also positive. So let's, for moving from A to E, how much work would be required? So from A to E, we're moving in the direction of the electric field, right? And so in that case, work would be positive, right? However, if you're moving in the direction opposite that the electric field wants you to move, like you're resisting it through an external force, then it would be a negative work. Okay, a point charge gains 50 microjoules when it is moved from D to G. D to G is negative 10 to negative 50. So negative 50, so we're going to do final minus initial again. So it'd be negative 60, right? Negative 60
Yeah.
volts equals um, work over, wait. Oh, okay. So you're just trying to find the charge, right? So you're trying to find Q.
Yeah.
So in order to do that, all you have to do is like just do a little bit of isolation. So if you really want, you can do negative 60 equals um, 50 minus 10 to the power of negative 6. And then you can divide both sides by negative 60. And it's what is that? Is that, wait, did I do that right? I don't know. 50 times the power of negative 6. Because that be like 0.83 something. Wait, okay, something's not right. Wait, let me redo that. So point charge gains, so from D to G. So G is negative 50 volts and D is negative 10. So negative 50 minus negative 10 is negative 60, right? So, oh wait, oh my God. Okay, so the mistake that I made was I did negative 50 minus negative 10 when in reality it's negative 50 minus a negative 10, which makes the minuses cancel out. Sorry about that. So negative 40 volts equals, let's say, 50 times 10 to the power of negative 6 joules over x coulombs. So once you solve that out, you should get 40x equals 50 times 10 to the power of negative 6, divide both sides by 40, and you should get that it's 1.3 microcoulombs because it's like it's about 1.25, I think, micro, but they just put 1.3 as like sig figs and stuff. So potential difference between B and E, that's just asking for you for the change in voltage. So if you look at E, it's negative 40 volts and B is 10 volts. Negative 40 minus 10 would be 50 volts. Is that the answer? I think. Yeah.
Yeah.
Okay. And then the last question says, how much work is required to move a negative 1 microcoulomb charge from B to D to C? So when answering this, I think the best thing you can do is just ignore the movement from B to D because it's asking you for your final destination versus your initial destination. So if you look at B to C, what's like a good reason that there's zero work done? It's because there's no movement in the direction of the electric force, right?
Yeah, I actually just calculated it out completely so that for B to D to C, from B to D to C, it makes a lot, it can show. So I calculated each of them out and did it mathematically and then added the two, and you end up getting 0.
Oh, really? Um,
Yeah.
okay, so even if you do it mathematically or even theoretically, if you look at like the final destination, right? Um, B to C is has zero change in voltage. So if you have zero change in voltage and the question is asking you for how much work is required, remember work is equal to um, voltage times Q, right?
Hmm.
Well, if the voltage
Yeah.
is zero, well, then the work is just zero, right?
The change in voltage is 0, so yeah.
Right. Sorry, the change in voltage is zero. Yeah, that's important. Okay, and then last question I think we should go over is 23. It says charge Q is negative 4.0 microcoulombs and it's moved horizontally. That means perpendicular to the motion of the electric field. So automatically when you see that and you know that work is FD cosine theta, um, the way I thought of it first was that it's cosine of 90 degrees and cosine of 90 is 0, which means 0 joules is done, right? Um, I guess
Yeah.
the other way you could think about it also is that it's like it's not in the direction of the force, and that's important. And yep, I think that's about it for today. So hopefully reviewing some electrical potential questions helped. Thank you.
Yeah. Thank you.